Okay, so we are the team Core Crunchers, and we have implemented a 8-bit CPU on FPGA. This is our block diagram of the CPU. So the architecture we will discuss sometime else in another video, but right now I'm going to run a program, execute it on our processor and check what we are getting at the output.
So here the program is written in the according to our user instructions. So basically for first line, basically move command is to transfer the immediate value into the register. So first we are transferring value 2, 4, 20, and all these values are hexadecimal. So all into the register. So R1, R2 and R4. Then this command is multiplication. Multiplication R10, R1, R1. It means multiply R1 and R1 and then store the result in R10 and R11. So basically multiplication is done on a 16-bit kind of basis. So lower 8-bit is stored in this one and the upper 8-bit is stored in this plus 1. So R11 will be upper 8-bit. And then similarly we have 3 multiplications.
Okay, so in this, next we have this
Load.
Next we have this load instruction in which we are loading the data present at the register address R12 into our memory location at 1000. Next we have this add instruction in which we are adding the values at register R2 and R4, and finally putting the answer into the register R20. Similarly we have subtraction, we have division instructions similar.
And the end we have the stop command to stop this.
To stop the program. So next what we are going to do is we are going to save this program. Next we have this compiler, Corel's compiler.py file, in which we have written our compiler. So I will just run this compilation process.
So it will basically convert our top level programming into the binary, basically binary numbers, which will be our instruction set for our processor.
Okay, so I'm hitting the run button. As you can see that the script.coe has been generated. This script.coe will be loaded into the processor for execution. So to load the program file into our processor, let's go to the block design. I'll just click once more on the open block design. Next I will just go to program memory. Let me show you our program memory. So yeah, this is our program memory, and in this option we have a option to load the memory with the initial script file in which we have written the program, we have saved it, and we are loading it with the script.coe file. So basically the program will be initially written in the program memory. Next we are gonna generate the block design for it.
So basically it will update all the block with our current code that we have compiled using our compiler.
True.
So after this, now our block level diagram is ready. Now we are going to synthesize our design for the...
Okay, one thing I'm going to ask to you. Have you disabled the simulation?
Oh yeah.
Okay.
So basically
initially we were testing it in the simulation. So we had a test bench, but right now we are going to implement it on the FPGA. On this FPGA. So we are going to disable our simulation file.
And after this we have to again rerun the block diagram.
Yes, and since we are disabling it, so we again have to rerun our block diagram. So the process that we just did, we will have to do it again. Okay, since it has been disabled, now let's go to open block diagram, go to memory, other options. We can see that the script.coe is still loaded here. We will click edit, just click save once, close, okay, and then we will again generate our block diagram again. Okay, so our block diagram has been generated successfully. Now I'm gonna run the synthesis process. Okay, let's hit OK. Okay, and right now, as you can see here, it is being synthesized. It's gonna take a while, so we'll be back in some time.
In that moment, I can explain what it is doing. Yeah. So it is basically mapping your input-output ports with our code. So we have decided to keep 3 ports. So you can also see it here, like when we go to elaborated design. So basically we are having 3 finally output port from our processor. Yeah, so as you can see we have basically 3 output ports. One is our clock, one is reset and start 0, and we have mapped these 3 ports with the hardware pin, that is H16, that is the internal clock of this FPGA board, M20, which is the switch 0. As you can see here, this is switch 0.
So basically this is the switch 0. Yeah,
this one, yeah,
switch 0, and switch 0 means M20. So M20 has been mapped to the reset pin, and this switch 1 has been mapped which is M19, which is mapped to the start pin.
So in this synthesis
So our
process,
synthesis process has been successfully completed.
So-
Now we are going to run implementation,
yeah.
right?
So implementation is basically converting all your code into the gates that are present inside this FPGA and like programming those gates internally, electronically. Sorry.
So as you can see, it is being implementing our design. It's gonna take some time, so we will be back in some time. Okay, so we are back, and as you can see that the implementation has been successfully completed by our software. Now we are gonna open our implemented design. Yes.
Expand this.
Just maximize that. Yeah.
So basically you can see this is our internal architecture of this FPGA chip. So internally our program has been programmed in this area, and the respective gate that has been affected due to our program has been highlighted here. So in this way this software basically implement all our codes and all our logic into this programming arrays.
Okay, so now we are done with the implementation part. So we are going to generate the beta stream that will be going to be written on this FPGA board. So I'll just go to this option, generate beta stream. Okay. And now you can see that the beta stream generation has been initiated and it's in the progress right now.
So this beta stream basically transfer all the logic from the software and tells the FPGA that which gate to be on or which gate to be off to like perform our logic or to perform our calculation according to the program written inside it.
Yes.
So it will take a time, we will come after that.
Okay guys, we are back, and now you can see that our beta stream has been generated successfully. Now what we are going to do is we are going to upload our beta stream into our device. So for that we are going to open our hardware manager.
So now, you can see here this board is having basically micro USB to this USB connection. So this is used to program a PCB, to program our FPGA. So basically we will connect our FPGA board to this PC. So you can see here blinking lights. So this blinking light shows that this FPGA is not programmed yet. Once programmed, this blinking will stop. So you can see here also in the software.
Right now no hardware is connected. So we are going to click on open target and click on auto connect. It will search for the connected devices and it will select our device that we have just connected to the PC. Now you can see that our Xilinx board is connected to our PC. Now we have an option to program our device.
So before that also I'm making sure that these both switches are off, because this is our reset signal and this is our start signal.
True. So what I'm going to do is I'm going to just hit program device button, program. So it will write all the beta stream that we have just generated into the device, and I hope yes, it is now programmed. As you can see that the status for the board is now programmed.
So also you can see these blinking lights have been offed in this device. And one more thing I want to point it out here, we are using virtual input output because the number of pins or the data lines we required is not available in this board. So that's why we have used the virtual input output. So first input output is basically what we are taking as output. So we are having the GPR data output and then memory data output both of 8-bit, and then accumulator data output of 8-bit, and then flag registers. So these four are our output for the virtual input output, and there are two inputs. One is for like GPR address, because we have 32 bits, so we have 5-bit as an address, and for the memory we have 16-bit address. So here, so these components are used to find the values of the internal register or memory during the runtime. So now you can see our program has been written inside this board. So now we will run our program. So before running our program, the clock has been internally given from this FPGA. To run the program, first we will reset our mode. So basically reset our program counter to 0 so that we can start our program.
So now we have reset our program counter, reset our processor actually. Now we are gonna give high input to the start button that will start the execution of the program in our processor. So okay, Now you can see that there are some changes in the virtual input output ports. Now I hope that the program is successfully executed on our processor.
Now we will verify our results according to the program.
Yes.
So we can see that the program that we have written, it is first to that it is basically moving the value 2 in R1 and 4 in R2 and 20 in R4.
So we are
first
going
we
to
will
check
verify
if
this value.
the register value has been updated or not.
So we will start with the value R1. So R1 basically 0 1. Okay. As you can see, the value 2 has been put into this register. Next
we have put the literal value 4 at register 2. So we are gonna put 2 to the address line, and we can see that the GPR output line has been updated to the value 4. That means at R2 register 4 has been written.
Similarly for R4 we can see the value 20 has been written. These all are hexadecimal. Our next operation is basically multiply R1 and store in R10.
So as you can see that the value of R1 was 2, and when we multiply R1 with R1, that is multiplying 2 with 2 will give answer as 4, and that will be stored at the register R10. So let's check it has been stored or not.
So we'll go to here, and here since it is an hexadecimal, so R10 means 0A. So you can see the value 4 has been stored here, that is the square, or basically 2 into 2. Next we have R12, that is R2 into R2. So this is basically 4 into 4, 4 into 4 cross 16. So 16 means in hexadecimal it is 10. So we'll check at 12. And also this is our R12. R12 means in hexadecimal we will have B. So sorry, it will be C. So we will see at 0C. So it is saying 10 means 16.
Yeah, basically it's coming out to be 10, and 10 if we convert this hexadecimal value to decimal, so that becomes 16, and as we know that the square of 4 is 16.
Now next we have R4 into 0A. R4 we have 20. 20, as if you can see in the hexadecimal, then this 20 is your
20
32,
basically means 32,
and 0A means 10. So 32 cross 10, it will be 320, and we should get the value, as you can see, for 320.
For 320 decimal value we should get 140 as hexadecimal number.
And now our program is something like the lower 2 bits will be stored in the lower 2 bits of this value will be stored in the data in the register that we have provided here, that is R14, and the upper 2 bits, that is 01, will be stored in the register R15. That is the next of this. So we'll check it. So first we will check for R14. 14, it means RCD.
D.
D.
No, it's E.
It's E actually.
So as you can see that at address E we have 40 data.
That you can
That
see the
means
lower,
the lower 2 bit of the result.
And then we have the next value, that is 10. 0F.
Click it once.
0F.
Okay. 0 and
F. And
now
we'll
you
be
can see
having
it is 1. So basically you can see that the MSB 01 and the LSB 40 becomes 140 hexadecimal number, that is nothing but 320 in decimal sense.
Yeah, and that is a multiplication of our 32 cross
10.
10.
Next we have loaded the value present at the register R12 into the memory location at 1000. So we are gonna check at R12 we had R2 into R2, which means the value is stored at R2 is 16, and in hexadecimal it is 10. So at 1000 memory location we must have the value 10. Let's check.
So this is our memory location line. So we will be writing 1000. So you can see it is 10, that is 16. So the memory data out is 16 here.
Up next we have this add operation, in which we are adding the value present at register R2 and R4 and storing the value in R20. So here we had the value 4 at R2, we had the value R4 20 at R4. So we have calculated the sum of 20 plus 4, which is 24, and stored it at R20 locations. Let's check what is present at R20.
So R20 here basically means 14. 16 plus 4, that is 20. So R20. So at R20 you can see it is R4. Similarly for the next we have R21. So R21 will be R4 minus R2. R4 is our 20, that is 32, and R2 is our 4, so 32 minus 4, that is 28. And if we can see 28 into hexadecimal, then we are having 1C. So 1C should be present as R21. So let's check. Yeah, so we can see RC. Similarly for the last operation, division R4 by R2. R4 is our 32, R2 is our 4. 32 divided by 4, it should be 8, and 8 should be present at R22. So let's see. 8. So these is so basically all our instructions have been successfully done, and this stop basically tells that the instruction has been completed. So yeah,
so this was our whole demonstration of our program executed on our 8-bit processor that we have designed. Furthermore, we will be discussing our architecture in some other video.
Thank you.
Thank you all. Let us introduce ourselves.
So it's me, Ankit Raj. I am BTech third year ECE in Indian Institute of Space Science and Technology.
Next we have.
I am Saurabh from BTech third year ECE.
And yes, I am Aditya Raj. I am a BTech third year student ECE at IIST.